Hello everyone, welcome to this session. In this session, we will continue to formulate various kind of engineering problems to optimization problems. So last class, we have discussed a dipole antenna, right? So this class, we discussed more than one antenna. So we have an antenna array. So what is array? Array is multiple antennas working at the same frequency are fed and spatially arranged. So as you can see, the blue board, so each yellow one on them, this is an antenna, and they work together as an array, right? So what we will see this case study is a circular antenna array. So circular antenna array means antennas are arranged in the form of rings. As you can see this figure, we can see each one of them, we have they are placed in the rings. For each of them, we have two design variables. One is I, one is beta. So what are they? The I is the amplitude of the array element feed current, and beta is the phase of the array element feed current, the I and beta, right? So these are the design variables. When we have the design variables, we need to see the design requirements. So here I listed them as follows. First of all, the side lobe SLL X is the design, should be not more than minus 20 dB. Directivity should not be less than 10 dB. The gain at the 180 degree should not be less than minus 0.1 dB. And the gain from 80 degree to 120 degree should not be more than minus 40 dB. So as you can see, these are really complex, right? Really complex. But you don't need to understand them, except you are an antenna engineer. So if you are a consultant armed with AI techniques to help an antenna engineer, you don't need to understand the details of this concept. You only need to understand what are the design variables, right? This is the first question. And the second is that what are the objectives and the constraints? So we can see these ones. We already know the design variables, and for these specifications or requirements, we need to consult ask the antenna designer how he or she would like to treat them. So we can see now that the designer said he's not sure about if the SLL can meet minus 20 dB. If not meeting minus 20 dB, he or she wants to see how small can it be, and then decide the next step, right? So this is an optimization problem. So here I show the response of the antenna using different AI techniques AI-based optimization techniques, and this is a response, right? Now we come back to formulate the problem. According to what we have just known, should the SLL be set as an objective or a constraint? Is an objective, right? Because the designer is not sure if he can meet the minus 20. So if he cannot, he or she needs to see how small it is and see the next step. This means we want to minimize the SLL, right, to see what happens. And for the directivity and the gain in the 180 degrees and 80 to 120 degrees, those are the constraints. So we meet the specifications, that is okay. And the design variables are the amplitude and the phase, right? So we can formulate the problem like this. So we can see the constraint optimization problem. The SLL is the objective function, and the dx, gx are the constraints, and the design variables are the x, right? So this is the first case, antenna array design. Second case, we still talk about antenna. We talk about the compact antenna design. So what is compact antenna? Compact means make the size small. We want to minimize the size, right? So compact antenna are widely used nowadays, for example, in the biomedical engineering. For its in-body or wearable, we wanted the size to be small. And for satellite antenna, we want the weight to be light, right? So these are the application of the compact antennas. So now we have a problem. The description is like this. We want to design a pie-chart tunnel, a compact one, and the design variables are these. So what are these? I draw it here. So these are the design variables. By changing these parameters, the tunnel will have different performance. So we have two design requirements. The first one is the magnitude of the maximum return loss. We have seen it, I think, already, right? The max S11 with the magnitude, it should be smaller than minus 9 dB in the operating band of the 4 to 10 gigahertz. The second objective is the size of the tunnel should be smaller than 400 millimeters square, right? Even when we meet the two objectives, the designer still hopes to further optimize them, right? There are specifications, right? And when we meet these two specifications, we still hope to further optimize them. Then how to formulate this problem? We can see the max S11 and the size. We have specifications, but when we meet the specifications, we still hope to further optimize them. So how to set this problem? Is it a single objective or multi-objective? So it's multi-objective because both of the F1 and F2, we want to minimize them, right? So two objectives. And they also have constraints. So both of the F1 and F2, they are also objectives and also constraint, we can see. So forming the problem can be formulated like this. The design variables are here, right? So we can see this is the problem, right? Okay, that's all for this session. Thank you very much. Bye-bye.